Hello, today we will see yet another relation between primal and dual, which comes in quite handy in solving some combinatorial optimization problems. So we start with a preliminary theorem which says the following. Suppose x0 is a feasible solution of the primal and y0 is some feasible solution of the dual. Then x0 and y0 are optima if and only if C transpose x0 equals B transpose y0. This essentially comes from duality. So it just says that if I take two solutions, if it turns out that C transpose x0 equals B transpose y0, then they are the optima. And similarly, if we take optima, then the costs are the same. So this direction is directly from duality. When it just says that the optima of the primal and dual are the same, the costs of the optima are the same. For this direction, so it again follows from duality with just a few more steps. Suppose we have this, we want to show that x0 and y0 are optima. Okay. Firstly, note that x0 is a feasible solution of the primal and y0 is a feasible solution of the dual. So, since both primal and dual are infeasible, primal and dual are feasible, primal cannot be unbounded, because if primal was unbounded, dual would have been infeasible, right? So, both primal and dual are feasible and bounded, hence both have optima. Okay. Now, from weak duality, we can infer that you take any arbitrary solution of the primal, C transpose X will be at most B transpose Y for any arbitrary solution of the dual, and in particular if you take Y0, C transpose X will be less than or equal to B transpose Y0. Okay, so the primal is bounded by B transpose Y0, and in particular since C transpose X0 equals this bound, x0 attains this optimum cost and hence x0 is the optimum of the primal. Okay. Now it remains to show that y0 is the optimum of the dual. But then again from duality we know that optimum cost of dual should be equal to optimum cost of primal, and since y0 attains this optimum cost, y0 is the optimum of the dual. Okay. So this essentially follows from duality with slightly more care for this direction. Okay. Now here comes the main theorem called the complementary slackness condition. So let's once again take x0, x0 and y0. This theorem says that This theorem says that C transpose x0 equals B transpose y0 if and only if a certain condition is true. What is this? So there are m coordinates, dual has dimension m. Now, so if I look at y0 will have m values, y01, y02 till y0m, and each of them is bigger than or equal to 0. This condition says whenever y0i is strictly bigger than 0, the corresponding inequality is tight at x0. So once again you are evaluating this inequality at x0. Okay. So that is what this says. When the dual variable is slack, okay, the primal inequality is tight. Now the same thing, it also means that not of this implies not of this, right? So whenever the primal constraint is slack, the corresponding dual variable should be tight. Okay, this statement has two things. When the dual variable is slack, the primal inequality tight. Now when the primal inequality is slack, then the dual variable has to be tight. Okay, because if this was slack and this was also slack, then this implication gets violated. Okay, one more pictorial way of looking at it. So the primal has m constraints, 1, 2, 3, m, and the dual has m coordinates, each of them corresponding to one constraint. When the dual is bigger than 0, the corresponding thing is tight at x0, and whenever while evaluating this at x0 you get slack, the corresponding dual variable is tight. Okay, so I'll now try to give a proof of this fact. Okay, so here we are. So there are two directions. This should imply this and this thing should imply this. Let's first look at the backward direction. Suppose the complementary slackness condition is true. Then we want to show, suppose the complementary slackness is true between x0 and y0. We want to show that C transpose x0 equals B transpose y0. So first note that let's rewrite C in terms of A and Y using this constraint. So A is of this form. Now how do you get C1? So you multiplied this with the first coordinate of y0, this with the second coordinate of y0, and this with the mth coordinate of y0. So C1 would be A11 times y01 plus A21 times y02, so on till AM1 times y0m. Similarly, Cn would be A11 times 1n times y01, A2n times y02 till Amn times y0m. Okay, this we know. Since y0 is a feasible solution of the dual, we have this association. Yes. Now what is C transpose x0? C transpose x0 is, again, just rewriting it, C1 x01 plus C2 x02 and so on till Cn x0n. Okay. Now let me just rewrite C1 with this entire thing, C2 with this entire thing, and Cn with this entire thing, and then group together whatever we have for y0. So what will we do? Like if I look at the coefficient of y01, so this thing is multiplied with x01, this thing is multiplied with x02, and this entire thing will be multiplied with x0n, right? So if I look at the coefficient of y01, it will be a11 x01 plus a12 x02 till a1n x0n, right? And that is just the first row of a multiplied by x0. And similarly, the coefficient of y02 would be the second row of a multiplied by x0 and so on till the coefficient of this will be the mth row of a multiplied by x0. So, and this is all we need to show this thing. So what is our hypothesis? Our hypothesis says that whenever this thing is strictly bigger than 0, this thing is equal to the corresponding b. So whenever something is 0, this thing anyway doesn't take into, it is not counted, and whenever it is counted, this is equal to bi. Okay, and therefore we get this thing. C transpose x0 is just y01 b1 plus y02 b2 plus y0m bn. Okay, so this shows this direction. Now we want to show the reverse direction, that is, if this is true, then this is true. So suppose C transpose x0 equals B transpose y0 for x0 and y0, we want to show this complementary slackness. And once again we make use of this fact that C transpose X naught is this thing. So let me rewrite it here. Now what do we know? We know that A1 X naught is at most B1, A2 X naught is at most B2, AM X naught is at most BM. So C transpose X naught is at most B transpose Y naught. Okay, but we know that it is exactly equal. So if one of these things is strictly less than the corresponding B coordinate, then the sum will be strictly less than B transpose Y naught. Okay, and since it is not the case, each of them that is counted in the sum should be equal to Bi. Okay, so that is why whenever we have Y naught I to be bigger than 0, we need to have the corresponding thing to be equal to Bi. So this is what I have written here. If for some I with Y naught I strictly bigger than 0, we have AIX less than BI, then when you add all of them, you will get C transpose X naught will be strictly less than B transpose Y naught. Okay, and this contradicts our hypothesis. And hence, whenever Y naught I is strictly bigger than 0, we should have equality. Okay, so this concludes the proof of this theorem. Now let us try to write a similar theorem for different primal dual pairs. So in particular, let's start with the primal including the X bigger than or equal to 0 constraint. Then how does the dual change? This thing is no longer equality and it becomes bigger than or equal to. Okay, and this thing remains the same. Okay, so these are tied with these constraints and these are tied with these constraints. Okay, and in this case the complementary slackness takes the following form. If we take a feasible solution of primal and dual respectively, now the costs C transpose X naught equals B transpose Y naught if and only if the complementary slackness holds for both these pairs of variables. Both these pairs. The first thing is for this. Whenever Y naught I is strictly bigger than 0, the corresponding constraint in the primal is tight. And whenever a primal variable is strictly bigger than 0, the corresponding dual constraint is tight. Okay, that is the thing. So this thing was not there in the previous case because here everything was tight. Now the proof of this proceeds as follows. Let's first try to do the backward implication. So we want to, given these two conditions, we want to show that C transpose X naught equals B transpose Y naught. Let's first write C transpose X naught. This is nothing but C1 times X naught 1 plus C2 times X naught 2 and so on, plus Cn times X naught n. Okay, so here is where we will use this condition. See, X naught 1 is either 0 or strictly bigger than 0. When it is equal to 0, this thing doesn't get counted, and when it is strictly bigger than 0, C1 can be replaced with A1 transpose Y0, right? Similarly, when this is strictly bigger than 0, this would be A2 transpose Y0. Okay, now this helps us rewrite this in this form. When this is 0, doesn't matter what we multiply it with, and when this is strictly bigger than 0, we have this we have this equation. So you can rewrite this as follows: X naught 1 times A1 transpose Y0 plus X naught 2 times C2, which is A2 transpose times Y0 and so on. When this is 0, this C2 may not be equal to this, but we don't really care. Okay, now once you have written it like this, you need to do some more rearranging. Okay, so I hope this equality is clear, and this comes from 2. Now how do we rearrange? So I want to collect terms corresponding to y01. So y01 comes with x01 times a11, and here y01 is multiplied with, this is what? This is the second row of A transpose, which means this is the second column of A, right? So A21 times y01, and here this will be this is what? This is the nth row of A transpose, hence the nth column of A, which will be A1n times y01, right? So here it was A11, here it was A12, and here it was A1n. So that gives us the first row of A multiplied with x01, x02, x0n here. So that is x0. Okay, so the coefficient of y01 will be the first row of A multiplied with x0. Coefficient of y02 will be the second row of A multiplied with x0, and so on. So this is just a normal rearranging. Now we can use this condition. So what does this say? This says that whenever this is, so this thing is either bigger than 0 or equal to 0. When it is strictly bigger than 0, this thing is equal to bi. Okay, so this helps us rewrite this sum as y01b1 plus y02b2, and so on. So terms which are, whenever y0 is 0, this will be 0, and if not, this quantity is equal to this quantity. Okay, and this is nothing but B transpose y0. So we got C transpose x0 equals B transpose y0 from these two conditions. This shows this direction, and for this direction you can employ a similar trick. So this part will come by the same arguments as previously, except that you have to be careful about this sign. And for this thing, you write something similar to this system starting from the primal. Okay, so that I will leave it as an exercise. Now what about a general primal? So in general, the primal can have either bigger than or equal to, and here you may have less than or equal to, or unrestricted. Okay, so let's consider a generic primal. So you maximize C transpose X subject to some AI X compared to BI, where where the comparison operator can be one of these three, and Xj compared with 0 could be either less than or equal to, bigger than or equal to, or I am writing this to say that it is unrestricted. Okay, now for some combination of operators you will get a primal, and for that there will be a dual, right? Now for a generic primal dual pair, we have a complementary slackness condition. So the dual constraints will correspond to the operators here, and the wise comparison will correspond to the operators here. Okay, now here is the general theorem. So let x0 and y0 be feasible solutions of primal and dual respectively. Then C transpose x0 equals B transpose y0 if and only if these two conditions are true. So you take the ith coordinate of dual and multiply it with the difference between AIX and BI, which is the ith constraint of primal. Okay, and that thing should be 0 for every I. And similarly, you take the jth coordinate of x0 and multiply it with the difference between the jth constraint of dual. That depends on how xj is. Now this can be either, this will be either less than or equal to, bigger than or equal to, depending on the constraint here. So anyway, so you take x naught j and take this difference, and this multiplication should be equal to 0. See, in the previous case, we had less than or equal to, sorry, we had less than or equal to here, and then the complementary slackness condition said that if this is bigger than 0, then this has to be equal to 0. Okay, that satisfied this. Similarly, when this was bigger than 0, we wanted this to be equal to 0. Okay, so that was the previous case. Now in the very first case, this was always true. Okay, and hence we had only this. Okay, so the proof of this is left as an exercise. It uses the same style of arguments, except that you need to be careful about the particular choice of constraint, the operator and the corresponding comparison for the variables. So if this was bigger than, if this is bigger than, then in the dual you will have negative, and if this is equal to, the corresponding dual variable will be unrestricted. You need to keep this in mind when you try to prove these two statements. Okay, and the proof is left as an exercise.